Alright, so today's topic is going to be work energy theorem, and we'll talk a little bit about thermodynamics. And yeah, okay, so first things first, work energy theorem. So essentially, work is defined as a force acting on an object over a distance. Okay? And it turns out that there's this idea called energy, and what energy is it's defined as the ability to do work. Okay, so I can provide force for a distance as long as I have a store of energy. Once my store of energy is used up, I can no longer do work in that situation. There's parallels to like real life, you know. If I eat a big breakfast and I have lots of energy from that stored inside me, I'm going to be able to work harder, than if I were to say not eat anything all day and then go and try and bust out 100 squats in the gym. I'm just not going to have energy to do that. So there is kind of like an overlap, to the real life concept of energy and work. However, in physics, obviously we're a little more strict about how we define these things, right? We remember that. Is this actually the full formula the way I've written this down? Right. So the cos theta that's added on here just ensures that, if for instance we're, I don't know, we'll say we're applying a force in this direction on some mass, and the mass is moving in this direction. Okay. Well, we can only talk about the component of force that's in the direction of motion. In this case, in the x plane. So that's why this cos theta is on there. So it's a little more, nuanced than just, yes, force over distance, that's it, we're done. Okay? It's the force in the direction that work happens. If we're, say we're just, holding up a barbell or something, right, over our head, you see like weightlifters get into this pose. Well, in everyday terminology, they're clearly working, right? They're sweating, struggling to keep this weight up. It's really hard to do, right? And eventually they drop it. Okay? We would say, well, they're doing work. It's hard to keep that weight up there. But in physics terminology, if there's no motion, no distance covered, they're not doing any work. Okay? And we also have this concept of negative work, right? If this guy lets this down slowly, he has to do so by still applying an upward force, just a slightly lower upward force. And as this comes towards the ground, right, he's doing negative work. Does negative work require energy? Yeah, any work requires energy. So we're going to get into this concept of work energy theorem, okay? And I'll just kind of lay it out there and we'll try to describe how it works. So essentially, doing work requires energy. And doing work can store energy. Okay, which is kind of interesting. So you need work, you need energy to do work, but you need to do work to store energy. Okay? Right? Okay, sort of. The weightlifter is probably not a good example because I'm trying to tie in like real life. So the question was, if I eat food, I store energy, and then I work out so I get stronger so I can do more work. Okay, that's the question. I liked where you went at the beginning. Okay, where do I get the energy to do work? I get it from the food I ate. Where did the food that I eat get the energy that it stored? How did the food get energy in it? Okay, if it's plants, it gets it directly from the sun, right? So the sun shines and plants have a way of, taking in the stuff around them and creating energetic molecules, right? And this, this essentially, these bonds inside this chemical contain energy that was originally in the sun. All right? Hope that our chemistry knowledge is up to date, so we kind of get what I'm talking about is photosynthesis, right? And even if I'm eating meat, right, the meat had to eat plants to get the energy that's inside the meat, right? So where does the sun get its energy? How does the sun get energy in it? Where does that come from? Nuclear fusion. Yeah, it's actually fusion. So we're going to get a little bit beyond where we need to go here. Essentially, what's happening is deep inside the core of the sun, where it's ultra hot, hydrogen is being fused together to make helium. How does that make energy? How does energy come out of this? So we've got one proton, actually two protons, and we got to get neutrons from somewhere. Interestingly, protons can be converted into neutrons, but we won't really go there right now. And at the end of the day, you get this kind of new thing that's sort of like this. I'm sort of glossing some stuff over. How does and massive amounts of energy radiate out of here? Energy just comes out of this. How? Yeah. Uh-huh. Right. 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 So what we're saying is, right, what the question was, or what the statement was, is that it takes lots of work to cram two protons together, and that's absolutely true. The question is, where does that come from, right? It takes lots of work to do this. Interestingly, though, this releases a lot more energy than the work that went into it, right? So it's actually like, if you want a chain reaction or a self-sustaining situation, kind of like a chemical reaction, in that the energy required to start the reaction is fed that energy from the reaction happening. Okay, does that make sense? Breaking apart elements that are lighter than iron, requires energy. Okay? In other words, fusing things together that are lighter than iron releases energy. Breaking apart things that are heavier than iron releases energy. In other words, there's this kind of flow in the universe towards everything becoming iron at some point in the far, far future. Okay, again, getting way beyond where we need to go. The question was, how does fusion, where does the energy come from that allows this weightlifter to pick something up? This is good. Like, I mean, we're talking about thermodynamics here, whether we know it or not, and some of the laws of energy conservation in the universe. So it's okay that we're talking about this. It's not what I really wanted to talk about, but it'll help us build in nature. So we'll build in later, okay? So again, this guy eats food, okay? Somehow he accesses the energy that's in food. That's chemistry, okay? But we want to know how the food got its energy to begin with, and we said from the sun, right? The sun allowed photosynthesis to happen, and that energy moved up the food chain and eventually ended up in this guy, right? Which he then did work to lift something up with, right? How is it that the sun is able to produce energy for billions and billions of years? How does that happen? Something to do with fusion, but what? Here, look at this. Okay, this is pretty famous. Essentially, what does the E stand for? Uh-huh. And the M? Mm-hmm. Yes, the speed of light. And it's a big number already, and you're squaring it. And so, how Einstein did this, please don't ask me. It's way beyond my ability level. But essentially what it's saying is that mass can be converted into energy. What's energy again? The ability to do work. But what is it? I don't know. Okay? But what ends up happening here is when you fuse these ingredients together, it turns out that the product weighs a little less. Okay? The product of putting hydrogen together to make helium weighs a little bit less. Okay? Yep. Yes. It doesn't work that way on Earth. If I take two eggs and I weigh them separately and then I weigh them together, the mass of the two eggs weighs the same as adding the two masses of eggs together beforehand, right? No mass is gained or lost in that scenario. But when we make helium out of hydrogen, the products weigh a little bit less mass in the products than there is in the ingredients. So, yeah, that's right. So the difference in mass between these two is converted through a formula, right? Not through a formula, but the formula describes how it's converted. And the difference in mass between the helium produced and the hydrogens that went into it, or the ingredients that went in, is what provides the fuel and the energy that's going on inside the cell. And it's a lot. Okay? There's a lot of mass difference here, and there's a lot of energy released by fusion, orders of magnitude more than for the changes in fission. Also, there's mass lost in fission as well, and that's what gives the energy released in a fission reaction. Okay, so let's just leave this behind for a minute. This is work energy theorem, right? It is energy getting released, energy getting converted, right? Energy being consumed, energy being accessed, and then work being done using that energy. Question. Yep. Mass and energy are two sides of the same coin. Okay? You can calculate the equivalent energy value for any mass. Yes. Yeah. You can try it. Put a kilogram in this and see what you get. See what a kilogram of whatever is the equivalent of in energy. It's a lot. So you could think of that matter as condensed energy if you want. That's one way to think about it. Okay. So work energy theorem. Let's do an example here. Okay. So a simple example. Let's keep it simple. Example. Okay. I like this concept of lifting something up. Okay. It takes work to lift something. Let's talk about that. Okay. So let's say here's the ground. Okay. Here's some mass. Ooh, it's an ugly mass. Wait, let's salvage the mass. There it is. Perfect. There's a mass. And for kicks, let's make this a 100 gram mass. You'll see why in a minute. Okay, so there's a 100 gram mass for 0.1 kilograms. Okay? How much force would it require for me to lift this up off the ground? How much force would it require for me to just stand there and hold this object? Let's say. Here I am. Holding it here does not require work, correct, but it does require force, right? How much force? Yeah, can we round a little bit here? Rounded, how much? Yeah, essentially 100 grams is basically 1 Newton of force, right? 1 Newton of force is required in order for me to hold this object still. So, how much force is required for me to keep this object in constant motion? Not accelerate it, but keep it in constant motion. Now, where did we come up with this, right? Let's just remind ourselves. Well, there's a force of gravity down, and that's equal to mg, and we're saying that m is 0.1 kg, and we're saying that g is roughly, it's 9.8 meters per second squared, but we're going to round it to 10 meters per second squared just to make this math easy. And that means that 1 Newton of downward force is acting on this object. And therefore, I need exactly 1 Newton of upward force in order to keep it still. The next question is, how much upward force do I need to keep it moving upward at a constant velocity? Not even point. Once it's moving, if there's 0 force, and there is 0 force, 1 Newton up plus 1 Newton down equals 0 newtons, it will stay at a constant velocity. Okay? Stay at a constant velocity. So once it's moving, it'll stay at a constant velocity. Yes, to get it going, there's a little bit more work required, right, to overcome the inertia of the object sitting still. We have to accelerate it a little bit. We're not interested in that time that we're accelerating it. We're just interested in now it's moving. Let's keep it moving, okay? And let's say that we move it up 1 meter. So it moves up 1 meter. What we have done is we've applied a force of 1 Newton for a distance of 1 meter. How much work have we done to lift a 100-gram object 1 meter up? 1 joule. You've done 1 joule worth of work. What weighs about 100 grams that you're familiar with? What's something in your everyday life that weighs about, 100 grams? It's not a pencil. Pencil weighs less. I have a great example. An apple. An apple weighs approximately 1 Newton. Okay? It's nice. Newton's associated with apples. You can think about an apple. Boom. An apple is about 1 Newton. So wrap an apple around your mind. That's what we're talking about. So think about lifting an apple 1 meter. If you lift an apple 1 meter, you've done 1 joule worth of work. Is that a lot of work to lift an apple? Not really. How many times do you think you could lift an apple up and down before you got tired? Oh yeah, lots, right? Lots and lots and lots, okay? Exactly. So now the question is, what can we think about once we've got this thing lifted up, right? So we know the amount of work that went into lifting this object is 1 joule, okay? So let's just recap here what the scenario is now. So now we've got the ground down here, okay? 1 meter above the ground, we've got a mass, roughly about the mass of an apple. And we know that in order to move it, the delta, or change its value 1 meter in this gravity field, it has to be in a gravity field or else this doesn't make sense, right? We did 1 joule worth of work. Okay, so let's write out what we've done, okay? We've said that to lift this up, we've gone mg, right? That's the force that we put on there, mg times the distance. Mg times the distance, right? That's how much work we did. The work we did here is mg times the distance, right? Force of gravity times the distance. Are you all on board with that? And that equals 1 joule. Okay, so 1 joule. Now that we've done this, okay, we can say this thing can do work for us now, can't it? Now that it's up there. Think about what it can do. What if I let it go and I put like a nail underneath it? What would happen when it struck the nail? It would apply a force times a distance onto the nail and push it down. It would do work on the nail. Or what if I were to, I don't know, put like a pulley here, wrap it over a pulley. Could I use it to, say, lift another object up in this scenario? Absolutely. I can convert the fact that I moved it up here and that it's hanging out up here into other forms of work. Could I make it generate electricity for me somehow? Sure. Take this off and attach this to some sort of dynamo or coil of some sort. Spin that as it falls, and I'll generate a little bit of electricity. Could I make a clock run with this? Absolutely. There's old-fashioned clocks that you lift a weight up, and that's essentially how it winds. Like a cuckoo clock is what I'm thinking of. It has those big, like acorn-shaped things hanging from it that slowly move down as the clock moves. So in other words, when an object of mass is up high, we can make it do work for us. Where do we see raised objects or raised something doing work for us a lot, especially where we live? I'm going to start drawing it and see if you can figure out what I'm doing. Ah, yeah, hydro dams, sure. Or like if you don't have hydro dams, like, for thousands of years, people have been accessing the energy stored in raised water to do work for them. Like, think about like a flour mill or any kind of water mill. Is that? Yeah. Yes. Yes. Okay. But that's different, right? Like the. Yeah. Mm-hmm. Mm. Yeah, absolutely. Historically, there's all kinds of ways that the energy stored in water has been used to do work, right? So if you can make something spin with water, then you can attach, machinery to that. You can attach hydroelectric generators to that. You can, there's nonstop ways you can think about that. Where does the energy originally come from to get water up higher, back here and over here? How do we get water up high? How do we lift it? Do we lift it? Do we? Ah, there we go. Yes, we use the natural process of evaporation, right? And the energy to evaporate water comes again from... So water's going to evaporate and it's going to fall as rain, right? Back over here. Is this how you make a dam? Well, I think it's a little more complicated than that. What's that? Well, okay. Well, no, not really. Like like it's going to evaporate everywhere. But remember that like a dam is put in a place where, you know, so like, I mean, if you look at, here, let's look at Manitoba, for instance, where we live, right? So we have lots of dams up here. And what's going on is water is draining off of like huge amounts of land, right? Following these rivers towards the bay, towards Hudson's Bay. So it's naturally flowing there, right? So we put dams on these rivers, right? And what that does is these naturally flowing rivers, right? The land is sloped down anyway, and the rivers are following the slope of the land towards the ocean, right? We know water flows to the ocean. So we put a dam there, that creates a lake behind here, right? Well, this water's still flowing, right? And it fills up this lake. This is where the environmental issues come in because you flood lots of land when you do this. But that's another story. We're just talking about the physics. And so, boom, this big lake kind of forms behind here. And then people like allow water to flow through the dam at whatever pace they want, right? This is all controllable. But yeah, that's the basic concept of a dam. So yeah, I mean, like evaporation is of course happening everywhere, right? But the amount of land back here that rain is falling on is much larger, right? And it's drained by all the little streams and so on. It's called a watershed, and it all flows in back into here. Like it's not like you can just be like, yeah. I mean, imagine that would be sweet. You could make like a little engine if you could just make evaporation happen on one side and have it come back in here. Maybe you could. Why don't you design something like that? Of course, you need lots of water to do anything useful with, right? Like, 5 gallons of water or 20 liters of water in a bucket a meter off the ground isn't going to do much for you, right? Why don't we figure out how much energy there is in that, though? Let's try that as a little exercise, okay? How much energy is there? So let's like say you set up a rain barrel a meter off the ground and you collect the rain and you want it to do work for you. How much work can you do in a full, 20-liter rain barrel? I mean, a rain barrel's bigger than that, like a 20-liter bucket. Okay, so here's your bucket. The sun did the work to fill your bucket, right? You've got a spout off the roof of your house. The bucket's full. Here it is. 1 meter off the ground. And this is going to be the power for your house, right? You're going to save these buckets raised up, and you're gonna allow the water to flow out of them through a little like tiny little generator that you've got, say from I don't know, an old toy motor or something. How much energy is there in this 20 liters of water right here? Okay, how are we going to figure this out? What do you think? So what we have to look at is we didn't actually have to do this work, but how much work would have had to have been done to get it up there to begin with, right? And this is our ground level, or our lowest state. By the way, is this level, right? Is this level like absolute? Like, is there always this level? Can you think like okay, so we've got this 1 meter above the quote-unquote, like, the ground. Okay, so this is like, if we want the ground state, it's literally the ground. Can I modify where the ground is, though? Yeah, sure. Like, I could dig a hole, and now this water is going to actually fall like 1.2 meters, right? Or I could put like another bucket like here. Now it's only going to fall like 0.5 meters. So it's essentially a little bit arbitrary that this is the ground. Like, we're saying this is the ground here. The ground isn't always, say, going to be 1 meter below. It's wherever we're measuring to, and it's not necessarily like an absolute scenario. We'll see a lot later down the road that the concept of ground also applies with electricity. Okay, but that's for later. So what we want to know is, for a 1 meter ground, water raised up 1 meter above the ground, how much work can it do? So the first question is, with 20 liters of water, how much mass is that? What is the mass of 20 liters of water? Let's just assume it's pure water so we can go by like what we already know. Right? So we know from before that 1,000 liters of water equals 1,000 kg, right? Or 1 ton, right? That's the original definition of the kilogram. So quick math in your head. What's that? Uh-huh. Yeah. So it's 20 kg. 20 kg roughly of water, which is like 44 pounds, if you care about pounds, which you should, but if you do, okay? So how much work can 20 kilograms of water, 1 meter off the ground, actually do for us? So how do we figure that out? Well, to get it up there, we would have had to apply how much force to it. How much force is there necessary to... What is the... If we want, what is the normal force, if this is on a stand, what is the normal force applied by the stand to this 20 kilograms of water? Yeah, it's approximately 200 newtons, and we had to lift it 1 meter, so there's essentially 200 joules inside of here, okay? Now you're probably asking, so what? What is 200 joules like? Well, let's do some converting here. 200 joules. It's fun to try to compare it to food, okay? So like in food, it turns out that there's about 4.1 joules in a calorie. Yes, in a calorie. Okay, and just for interest's sake, why don't we talk about the calorie for a minute? So what's a calorie? Good. Yeah, exactly. So 1 mil of water is equal to 1 gram, okay, essentially. And if we want to raise 1 gram of water 1 degree Celsius, so we want to take it from, say, 20 to 21, okay, well, that is going to require, that requires 1 calorie work, okay? Calorie is not an SI unit, though, the joule is. This also requires 4.1 and change joules of work, or energy is maybe a better way to talk about it. So it requires 1 calorie of energy, or 4.1 joules of energy. They're both units for the same thing, okay? One is just, I don't know, outdated. It's outdated, but it's still used in like food situations. Now, why is it 4.1 joules? Because it takes, that's the definition of the heat capacity of water, takes 4.1 joules per gram per degree Celsius. Oops, I didn't do that right. To raise water, right? So 4.1 joules go in there. So that's the kind of overlap between the joule and the calorie. So that is defined as 1 calorie, or 4.1 joules. Okay. Now a food calorie is actually 1 kilocalorie. Okay. So 1 calorie of food is actually 1,000 calories. So if I eat a Tic Tac, which has how many calories? 2? I don't know. They used to have commercials where they're like, there's only 2 calories in a Tic Tac. It's actually 2,000 calories is what they need. 2,000 real calories. So food calorie is actually a kilocalorie. That's a food calorie. So, like, what's something that you know the calorie count of? Do you know anything? Let's find something. We'll pause for a second and go find something. So we just looked here, and we found that a cheeseburger from one of our favorite restaurants that starts with M, and it's not a very big cheeseburger, in my opinion. No, it's not that one. Cheeseburgers are quite flat and highly addictive and delicious, and occasionally they get burgled. Okay. We just looked it up, and it has 313 calories, which we just realized is actually 313,000, right? Real calories, which is multiplied by about 4, right? What's 4 times that roughly? So 313 times 1,000 times 4. Does that seem right? Is that not right? Times about 4? About 1.2 million joules, is it not? Is my math wrong there? Yeah. Yeah, I think my math's right. Right? That's calories. It's just written as calories, but it's actually kilocalories, right? So when they say calorie, they mean kilocalorie, and there's 4 times, roughly 4 times the number of joules in a kilocalorie. But 1.2 times 10 to the 6 joules. Okay, so you eat 1 cheeseburger, and you have ingested enough energy to do this 10,000 times? Seem about right? 6,260 times lifting this water from 1 cheeseburger. So I mean, yeah, so this is 200 joules. This is 1.2 million joules. So 6 goes into there. So 6 minus 2, 654, 6 times 10 to the 4, right? So that's 60,000 times? Does that make sense? Sorry, 6,000, okay. Stupid extra numbers. But that, okay, so I mean, what does that really mean? Like, if I eat a cheeseburger, can I actually go out and lift a pail of water 1 meter up 6,000 times? Good. So here's the thing, right? Yeah, this much energy might be in there, but how much of it is actually accessible and usable? A lot it is. Yeah. Well, yeah. So there's part one, right? You're not just putting your energy into like lifting stuff up, right? You're putting your energy into like body functions, homeostasis, right? Your brain thinking, right? All these sorts of things are using up some of that energy. But I mean, you're also going to go to the bathroom at some point. Not all of what is in there is actually accessible to you, okay? However, when you start to look at the numbers of it, it's not too hard to understand why. If I go and smash 4 cheeseburgers or more, which I could easily do, but then I don't go out and lift this, you know, a few thousand times, why I have trouble fitting into my pants before too long, right? My body is very good at storing energy in fat cells, right? And I actually will start to expand right before your eyes if I continually eat cheeseburgers and I don't work it off. Now, the interesting thing is, it's not really, at the end of the day, about what I eat. I mean, that does play roles because there's other problems, but if you're just simply looking at the energy systems, if I take in 2,000 calories of cheeseburger versus 2,000 calories of, I don't know, well, yeah, lettuce. I might have to eat a truckload to get 2,000 calories from lettuce, but really, if we're just simply looking at the energy systems, energy in and energy out, it's not really too much about what I eat. So people are like, oh, like, you know, if you eat cheeseburgers, you're going to get fat. You're not going to get fat because it's a cheeseburger. You're going to be fat because it has so much energy packed into it, right? Meat has lots of energy. Fat has lots of energy. Sugar has lots of energy, right? So our body's interesting, right? Like you can feel full by stuffing your stomach with lettuce. However, it's not as satisfying as stuffing it with meat, right? There's other stuff at play. Okay, so we're off topic. It's interesting to look at the numbers and think about what's going on, but let's go back and let's talk about thermodynamics really quickly, because that does play a role. And we're kind of running out of time. This has been long already. But anyway, uh, thermodynamics. So this is the sort of branch of science that looks at energy transfers. It's kind of big around the Industrial Revolution, when people were figuring out how to take stuff like burning coal and transform that into useful work. So running like big cotton mills on steam power, getting steam engines to, take over for the work that used to be done by, people or horses or animals and so on. So they were looking at the science of things like, what happens when water, flows down a hill? How can we access that? What happens when we're burning, wood or coal or something in our boilers, right? And we're using the compressed steam here to run, like pistons and so on, right? And make big, mechanical Victorian industrial machines, run and spew steam out, right? So thermodynamics is like the study of energy transfers. So the first law of thermodynamics is that it's a conservation law. Energy is never created or destroyed, but only converted into other forms. Okay, that's the first law. And the second law is no energy transfer is 100% efficient. Okay, some is always lost, to various forms, but to some of the forms might be like friction, which creates heat, or heat directly. There's other ones that are like more nuanced when you're talking about like the way that electricity moves around and that sort of stuff. But I mean friction and heat, etc. Okay. So an example of this, right, is this scenario. So let's say we take our mass here that we've had before, and it could be water, it could be our weight, and we lift it up, 1 meter. Well, in order to make that get up there, okay, the math says 1 joule is required, okay? However, in reality, you are not just lifting in a complete vacuum, right? You're fighting, say, air resistance. The energy from your body is also going to create heat as you work, right? You get hotter and hotter and hotter, right? That is a form of energy that is not going into lifting the object up. So when I bring it up here, okay, although, mathematically now there's 1 joule in it, it probably took a little bit more than 1 joule in order to get it up there, okay? And it's where the concept of efficiency comes in. How efficient, is the human body at using its energy? How efficient is a car at, turning its gasoline, the energy inside its gasoline, into motion, right? Yeah, well, some more than others, right? Some cars are more efficient than others. So now that it's up here, let's say I let it go. Okay, so I drop it to the ground. And let's say what I'm doing is I'm driving a nail with it, right? I'm allowing it to fall to drive in a nail. Well, you have to apply a force over distance to drive a nail. What would happen if I let this fall? Okay, if I let it go. Would it, like, let's say this nail requires exactly 1 joule to push into the surface, right? Requires, say, a force of 1 newton, or sort of 10 newtons over 0.1 meter or something like that, right? It requires 1 joule. I have 1 joule. Will this system be able to drive my nail completely in? Okay, no, that's right. That's the second law of thermodynamics. But how can we wrap our brain around the fact that even though I have 1 joule here, and I got 1 joule, just for the record, we'll introduce this concept in a minute. We'll say it has gravitational potential energy. How I got that was I did mg, that's the force, times a distance, right? That's how I got it up there. So that's the amount that I have, just simply based on it being up there. If I let it go, though, the second law says I cannot convert all of this potential energy into work. Where does some of it go? Have you ever hit a nail then touched it? What does it feel like? Yeah, you bet it is. It's always hot. Okay? Hot. Sound. Right, we haven't got to waves yet, but sound is waves, like leaving through the system, right? Heat is the vibrations of the molecules that make up the air, or the elements that make up the metal, right? So um, yeah, like there might be, yeah, true, like there might be some bounce. I'm not sure exactly how to work that in because I know it would fall back down again. Let's not talk about bounce right now, but let's just talk about the general concept, right? In an ideal world, in an ideal scenario, I can transfer 100%, but in the real world, that's not how it works. Okay, so that's laws of thermodynamics and work energy theorem. Let's talk about the types of the potential energy that I can have. Okay, so doing work can store energy. Let's look at that quickly. Doing work can store energy. Okay, so you get this word potential, right? Potential energy. Well, what do you think the potential is? The potential to do what? Right. Potential to do work. So if I have the potential to do work, I have potential energy, right? So one type of potential energy is EG, which is gravitational potential energy. We already talked about this, but gravitational potential. Okay, how do I get gravitational potential? I work on an object and I lift it up, or something works on it. It could be the sun, it could be whatever, right? Something lifts an object up high. An object is up high, has some distance above the ground, and it has mass, it has potential energy. And we can figure out very easily what that is, right? F, G, times however high it is above the ground, tells me how much work I would have to do to get it up there, right? And therefore how much potential energy it has to do work when it comes back out. So EG is mgh. Well, height, right? Because now the distance is actually a height. Okay, so we remembered as EG equals mgh. H is the distance, but it's height. It helps us remember that we're talking about gravitational potential energy. Does that make sense? Perfect. Okay. The next one we'll talk about is kinetic energy. Okay, so it's not the fact that this is up in the air that's doing any work in this nail scenario we've been talking about, right? It's not about how high it is, because that's not directly what's going on. What happens as I let this go? What happens to the mass itself? Right. Gravity applies a force times a distance. Okay, actually, and VD, right? Applies a force over a distance. And what happens to this object? It starts to do what? Yes, it gains a velocity. Okay, so a mass that's moving has the ability to do work, right? A moving mass can drive in a nail. A moving mass can make a turbine spin, and so on. So what we're saying is, before the water starts flowing, before the mass starts dropping, it has gravitational potential. That gravitational potential, though, when we release it, is converted into another form of energy, the energy of motion, kinetic energy. Okay? So EK equals 1/2 mv squared. And where did we get this from? Well, gravitational potential energy was turned into it. It converted from one form to another, right? And when you think about it, that makes sense. The height is dropping. Energy can't be created or destroyed. As the d part of this gets lower and lower, this shrinks. Well, where does it go? It becomes something else. It becomes the motion. So where does this come from? Let's talk about this. Okay? So if I have an object, in space, and I want to get it going, I want to give it some velocity. Okay? I want to give it some velocity. We have a couple formulas for talking about that. We have Vf squared equals Vi squared plus 2AD. Well, you guys write this a little bit different, don't you? You write it as V squared equals U squared plus 2AS. Okay? Which means that, if initial velocity is zero, the velocity that this has is equal to its acceleration times the distance that we moved it over, right? You have this from your kinematics unit. Okay? Yep, there it is, right on the board. Okay, so let's think about this in another way, though. In order to get an acceleration, right, F equals ma, this has some mass, and we moved it some distance, right? We moved it some distance. So let's look at this formula up here. What if we do a little rearranging, and we say that, could we say that the acceleration in this formula is equal to v squared over 2 times s? What's that? What am I doing? I'm just rearranging this formula. That's what I'm trying to do. That's what I'm trying to do. So let's take this and let's substitute it in for the a, right? We don't care about a. A doesn't really matter to us. We want to know that once this has been done to it, and it has a velocity, right? How much energy was put in here, or how much, sorry, that's not right. How much work was put in here, and therefore how much work was converted into energy of motion. That's what we're after, right? We don't care about acceleration. We want to talk about it in terms of work. We want to talk about it in terms of the velocity that it has at the end. So then F equals m v squared over 2s. Well, we're saying d, but really we should be saying s, times s. So the s's are going to cancel off, and we're going to end up with this, ooh, that should be e, not f. Sorry guys, that should be e, not f. F is in here. Whoops. E is mad. Okay, mass times acceleration times distance. Force times distance. So what we get at the end of this, okay, once we've crossed that off, is we get actually our formula that we want, right? We get that the energy of the motion, being the work that we put in, should be equal to mv squared over 2, or as I like to write it, 1/2 mv squared. Okay, so what we've done is we've taken kinematics, and we've said this amount of work has to be done to get this object to whatever velocity it ends up at. Okay, if that much work was done, then that much work must be able to be got back out. Of course, second law of thermodynamics won't allow all of it to come back out, but in the ideal scenario, that's how much work comes back out. Okay, so this is the energy associated with a moving object. Okay, let's try something with this. Let's try a little scenario. How fast will a 30 kilogram weight be traveling when dropped from a 5-meter height? Just as it strikes the ground. Well, before you would have done a problem like this with just straight up kinematics, right? You would have, first you would have figured out what the acceleration is when you know what it is. Okay, then you would have applied a formula and you would have worked it out. Well, what I want you to do is try it in a slightly different way. Well, what we're going to say is the gravitational potential energy is going to all be converted into kinetic energy. Okay? Gravitational energy, what did we say that was? That was mgh, and that's going to get converted into kinetic energy, 1/2 mv squared. So here's this big, heavy weight. It's 5 meters up in the air, and we let it go. Well, it's obviously going to accelerate towards the ground. Do we know that when we're finding velocity at the end of this, does the mass matter in this scenario? Does it matter if that weighs 10 kilograms or 20 or 100? No, all objects accelerate at the same rate. You'll have the same velocity at the end. Yes, and this is borne out, right, by this equation. Mass is irrelevant. Okay? This is kind of, hopefully, this is helping you make sense of some kinematic stuff that we talked about before, right? So what we have then is we have that GH at the end of the day is equal to 1/2 v squared. Or, if you want to rearrange again, v squared is equal to 2gh, or at the end of the day, v is equal to the root of 2gh. You ever seen that before? You haven't? Well, let's figure this out, and I think you have. I disagree that you haven't seen this before. Root 2, 10, height 5, what is that? 50, 100. What's the root of 100? So what? What were you saying? Ah, okay. So there we just figured it out with energy equations. But energy equations actually turns out are really kinematics equations. Okay? So look, Vf squared equals v, or sorry, oops, I gotta use the right units here. Well, there's no initial velocity. There's our height, 5. There's the acceleration due to gravity, and there's the 2. Okay, so you're going to figure out the same thing, just using different methods. Okay? I think that as you work through this, you'll find that energy, concepts of energy, at least in my mind, they simplify things. There's less steps to consider, right? The formulas, I think, are simpler. If you know your energy conversions and you know your types of potential energy, you can essentially solve a lot, anyway, of kinematics problems using these units and do a whole lot more. Okay? So there's our big lesson for today. It was long and it was hard, but now you can finish those booklets that I gave you.